colloquium Quantum Contextuality in Quantum Mechanics and Beyond. It's my great pleasure to announce our speaker today, Philippe Grangier of the University of Paris Saclay. And today, Philippe will talk about contextual inferences, non-locality, and the incompleteness of quantum mechanics. So, Philippe, the floor is yours.
Okay. So, sorry, there is something not satisfactory. Let's try to. Oops. Okay, can you see my screen?
Yes.
Okay, I just try to go to full screen. Okay, still okay?
Yes.
Okay.
The bottom of the transparency cannot be read. The last line probably.
Okay, so the last line is the archive reference. So you don't see it? So I can do it this way.
I see it.
Maybe.
I
Okay.
see it full screen. So I don't. That is your local problem.
Okay, I check. I will check it.
I think it's a Zoom sidebar. It will disappear in a moment if you will not.
Yes, you may have your menu
Aha,
there.
you may be right. Thank you.
Okay, so Etibar gave the title, which is written here. So actually, it's very close to a talk I gave in last VATIO conference last August, but many of you were not there, unfortunately. So this, I had many discussions with my usual colleague, and the paper is on archive, just accepted this morning in Entropy. Okay, so as you know, I started my physicist life as an experimentalist, working on Bell's inequalities test under the supervision of Alain Aspect. So this was in 1980, 40 years ago now. And you also in 2015, there were these so-called loophole-free Bell tests, 3 of them in 15, 1 more in 17. And Alain Aspect wrote this paper in physics. By closing 2 loopholes at once, the 3 experimental tests of Bell's inequalities remove the last doubts that we should renounce local realism. This also opens the door to new quantum information technologies. So the conclusion is that we have to basically renounce local realism, that is, Bell's inequalities are violated, therefore Bell's hypotheses have something wrong, are untenable. And so since I started my life, my physicist life on that, I would really like to know what is going wrong. And this is my motivation here. So a good way to start is to ask John Bell himself. So he wrote in this book, Speakable and Unspeakable, let us anticipate that quantum mechanics work for us. My Bell's inequalities are violated. Where do we start? So there are 4 attitudes that could be adopted. The inefficiency of the counters and so on are essential. So these are the so-called loopholes. So this doesn't work. The loopholes are closed. So next one, there are influences going faster than light, even if we cannot make superluminal telegraphy. Actually, Gisin and company have shown that these influences should be instantaneous. It's even worse. So okay, this is an option. Another option is that there is this random choice, as you know, of the orientation of the polarizers, but actually these supposed random are not random. Everything is predetermined, superdetermined. Then Einstein locality can survive, but apparently everything is entangled with everything. So it's a so-called no free choice assumptions, which is really, I must say, then the whole analysis can be ignored. The lesson of quantum mechanics is not to look behind the prediction of the formalism. Well, that's quantum mechanics. Okay, so obviously none of this makes me happy, as you can understand. So my the approach in this paper will be to go one step back and to try. So the first one is out. but to give a mathematical content to all the 2, 3, 4. So let's start with, for instance, faster than light influence. So I think it can be written mathematically, and it can be called elementary locality. So I will define exactly what I mean by that. So you can get elementary locality, you can violate elementary locality without faster than light signaling. This can be done. So this would be an option. Then the second option would be the violation of what is called free choice, that is the existence of random independent events. So if there are no free choice, obviously these three be written mathematically. And the bad one, or the strange one, is the fourth one. So what I want to have, because it just says quantum mechanics is right, but I would like to show that it can be given also a mathematical content that I will call predictive completeness. This is a strange thing because actually it cannot really be formulated in a classical or deterministic framework. And this is, according to this would be my point, this is what is violated by quantum mechanics. But it has to be defined in some sense non-classically, and then quantum mechanics violate. But I will make it more precise. So what is this predictive incompleteness or completeness? So these words were introduced by John Jarrett in '84 in this paper. I think the idea is very interesting, but it was not fully exploited at that time. First, it's a little bit of an heretic idea. Because Bohr answered Einstein, Podolsky, and Rosen by saying that quantum mechanics is complete. It is complete that in the sense that if you are given a state with vector psi, you can calculate the probability of any other states phi that you may find in another measurement, which is the square modulus of the scalar product. So since you can calculate everything you have to know, in some sense, psi is complete. So this is a point where I will sort of disagree. The usual claim, the unusual claim, which was already done by Jarrett, is that psi may be predictability incomplete. So incomplete means that given psi, one needs to specify a full measurement in order to obtain a meaningful probability distribution over a set of mutually exclusive events. In some sense, the square modulus of the scalar product is not a real probability, because the phi may be anything. It does not have to belong to a set of mutually exclusive events. If you want to specify also a set of mutually exclusive events, you should not specify only one set, but a set of orthogonal states. So you have to specify actually a non-degenerate operator admitting phi as an eigenstate. And this is just what I call a context. So in some sense, phi or the set psi is predictively incomplete because you forget about the context. So this is probably not very clear at this stage, but I will come again and again on this point. So let's go. Okay. So my framework will be as general as possible. Okay, I discussed that a little bit with Etibar already. So it's mostly inspired. It's already in James. So, extensive use of conditional probabilities. And I would like to have it valid for QM and for hidden variable theories. This is why it is general. Then I will progress, introduce hypotheses, more and more hypotheses, and see where it splits, where basically the discrepancy appears between classical and quantum physics. So I consider the standard EPR-Bohm-Bell scheme, polarization measurement, some hidden variable small lambda, variable space big lambda, measurement by Alice and Bob with orientation X and Y, and binary result A and B. So according to Jens and others, and Jarrett, etc., many people wrote that, one can write the following relation between conditional probabilities. So what I want is the probability to get the result A and B given the orientation X and Y, but I can see that by introducing some variable, lambda, and I specify first lambda, and then I multiply by the distribution of lambdas. So this is very, very, very general. There are some cases. So I discussed, there are conditional probabilities. So you have to be careful that the conditions are defined and also that everything commutes, etc. So you have to use it carefully, but I will try to always use it carefully. That is, always use it when all these probabilities are defined. So lambda specify whatever may be specified about the emission of the pair in a given shot. So it's lambda corresponds to a given shot, given run of the experiment. Lambda may include variables which fluctuate from shot to shot and other variables that don't fluctuate. In this form, it is also true for QM, and in that case, there is only one variable, which is just the quantum state psi. It is also true for demonstration of Bell's inequalities using stochastic variables, the so-called Clauser-Horn demonstration. But obviously, there are subtleties because QM is not the same as Clauser-Horn. It is also true for theories where A and B are deterministic functions of lambda, X and Y. But as you said, determinism will be important, but I will also come back to that. I just want this thing to be as general as possible, and I think it is general enough for my purpose. Okay, so then we will introduce physics and restriction. So the first restriction is often called freedom of choice, which is to assume that where the functions are emitted, the values of lambda, which describes the emission of the photons, does not depend on the variable xy representing the settings. So it means that you have something like that. The P of lambda xi, xy is just P of lambda. And so my general formula, the previous one, this one, simplifies. There is only a P of lambda here. So you don't have to accept that. This is not accepted by super deterministic theory like Gerhard Tuft, as you know. Then because he assumes that all these random quantities, supposedly random, are related by some common path. Then it doesn't work anymore. This is this super deterministic theory. So you can use them if you like them. I will not do it, but I will come back to that at the end. So I assume that this freedom of choice is true, which means that the lambda, x, and y are really independent random variables. Now it's a little bit simpler, and now we have to focus on this conditional probability, which is P of AB given the orientation and the hidden variable. So something we can always write due to conditional probability is something like that, which is that you can split again this probability in two parts. This is something which is on Alice's side, so I can show it. On Alice's side, you have this probability for Alice to get result A for input X and also Y. And so, okay, that's fine. And this one is more interesting. It's a probability for Bob to get result B for input Y, calculated by Alice, because Alice knows X and A. If she measures X, she gets A, so she has this information, and so she can calculate this probability. So it's an inference. It's something which is calculated on Alice's side, and this will be very important. And obviously, Bob can do the same, but it will be a different splitting. So this is the probability for Bob to get the result B, and same thing, this is the probability for Alice calculated by Bob. And this is always true, basically. This is also true in quantum mechanics, and I will specify that. So we are still in a very general framework. So let's specify more. Now we can introduce something very, very important that I call elementary locality. So it's pretty obvious. It just means that the probability for Alice to get A does not depend on Y, which is Bob's orientation. Otherwise, it would be bad. You could do a faster than light transmission at the lambda level. And same thing on the other side. So we call this condition elementary locality, meaning that it is fulfilled for each given lambda. As a consequence, then it simplifies more, and then you have just X here and just Y here. So you can actually violate this condition without transmitting faster than light messages, because if you assume that you have no control of lambda, if lambda is completely random and uncontrollable, then you cannot use this thing to transmit information. But still, at the elementary level, you have this violation of locality if you don't admit that. So this is why I call it elementary locality. So all this agrees with QM. Quantum mechanics agrees with elementary locality. So this is still true for QM, and therefore Bell's inequalities cannot be obtained yet. Now, what is missing to get Bell's inequalities? If you want to, Bell's inequalities, if you want to get them, you have to remove XA here, and you have to remove YB here. But why? It's not, so Bell will tell, okay, it's non-local. No, it's not really non-local, because it just means that Alice is using some information she has to calculate a probability for Bob's result. So it's not an influence, actually, it is an inference, and I will come back to that later. So so far, it does not, according to me, entail any influence from one side to the other side. And so this can be true, and you still don't have Bell's inequalities, and everything I wrote so far agrees with quantum mechanics. So at some point, you must do something which does not agree with quantum mechanics. And so this was discussed by Jarrett and company. So there is still a missing step to reach Bell's theorem. And so the idea is that in order to Bell's theorem, you need two conditions. You need elementary locality, so I kept it, so that's fine. But you need another condition, which I call predictive completeness, which is the essential point here, which is that here you have to remove the A. And on the other side, for B, you have to remove the B. So now, yes, so just remind, if you take these two conditions, now that's fine. You get Bell's inequalities. If you have both EL and PC, this implies Bell's factorization condition, which is this one, and then you get Bell's inequalities. So since I told before that quantum mechanics agrees with elementary locality, then it must violate PC in this framework, because Bell's inequalities have to be violated. So now a little bit of terminology. So in the literature, these conditions have different names. So these were the names introduced by Jarrett, but Shimony wrote a paper where he called that parameter independence, and he called that outcome independence. So they are the same equations, actually. Physically, I really prefer these names, because outcome dependence or independent, it's really strange, and I would be in trouble to explain what it means. Whereas I really try to explain completeness means. So this is why I prefer to use Jarrett's terminology than Shimony's. Okay, so now, in order to violate Bell's inequalities, QM must violate predictive completeness. So it means that you have, this should be different from that, and this is equal to that due to elementary locality. So what should I say? So if you look at lambda as psi, as a quantum state, it means that by knowing A, Alice knows more than initially. So given x, y, lambda, she does not know everything. Something is missing. So what I tell, this is why I like this name of predictive incompleteness. The description given by lambda, or psi in the quantum case, is not complete. And knowing XA does bring something new to Alice. Then condition is related. Alice makes a contextual inference about Bob's result, and same about about Alice, and then Bell's inequalities are violated. So in order to make sense of this idea, it is essential to realize that contextual inference is non-classical, and also that it agrees with relativistic causality, and we try to explain that now. So yes. So in classical physics, condition PC is verified, and Bell's factorization follows, okay? But in quantum physics, again, knowing Alice measurement result, when Alice knows what she measured and what she got, she has one more information that she can use to make this contextual inference without invoking any action at the end. This is because Psi does not tell which measurements are actually carried out by Alice and Bob, and then Psi is predictively incomplete. Adding this information where and when it is locally available improves Alice's prediction about Bob's result and Bob's about Alice in agreement with equation 5. This effect, what is important is to understand that this effect does not show up in classical physics because lambda, in classical physics, lambda is predictively complete. You basically determine the result. So it's even, it's actually obvious in the deterministic case. If the result x, y, AB, sorry, are deterministic function of x, y, and lambda, it's clear that the lambda or whatever is predictively complete. But again, it does not show up in quantum mechanics because the quantum psi is predictively incomplete as long as the Schumann context has not been specified. So you see, it sort of identify the missing point in quantum physics, which is again that given psi, you don't know everything because you don't have a complete probability law over a set of mutually exclusive events. So also, since contextual inference only applies to probabilities and to inferences, it does not involve any physical interaction outside lat cones. So therefore, obviously, it obeys relativistic causality, and then it sort of explains why quantum mechanics has this sort of, peaceful coexistence. Shimoni was telling that, he was speaking about peaceful coexistence, but in that case, peaceful coexistence is rather obvious because since elementary locality is verified, then there is absolutely no reason to contradict relativity. So a typical wrong line of thinking would be to say, if Alice can predict with certainty some result by Bob, a perfect correlation, for instance, then either Bob's result is predetermined, but then you are stuck because you have Bell's inequalities, or there are instantaneous action at a distance. Okay, well, you may like it, but you don't need it. This is my point. And this dilemma only applies in a classical framework where particles properties are defined in an absolute way and where Bell's inequalities do apply. So it's nice to make a little light cone picture to see that and to verify that there is no action at a distance. So this is shown here. So this is time space. So okay, you have here the emission with some determined by lambda. The choice of x, which can be an independent random event, as I assumed. And then, okay, this is time. And at some point here, Alice makes her measurement. She gets her result, and she can calculate that, which is this inference about Bob's result. Bob's result does not care about it. This is the essential point. It may have been done or not done or whatever. This is just an inference which is allowed to Alice because she got an extra information, which is X was already there. It was chosen here, but A is a new information, and then she can use it for making this contextual inference. Same thing for B. And then what will happen? So as I say, Bob's result does not care about this probability. It's not an inference. And actually, Bob can measure anything. So what is the use of this prediction? They can be verified, but they can be verified only this zone, which is the common future of Alice, Bob, etc. So the resulting prediction can be checked in the verification zone V in the common future of all light codes. So you see, there is no, the big thing is that this is an inference, not an influence, and then everything sort of runs nicely, in my view. Okay, so summarizing a little bit, the violation of Bell's inequalities can be explained by considering contextual inference, which in turn are allowed by the predictive incompleteness of the quantum state. So getting actual probabilities, not the So a colleague of me, Roger Ballian, called that Q probabilities, which are this square modulus of scalar product, which are not really probabilities as long as you did not get a full state of mutually exclusive events. This is my point again. So okay, this is written here. Similar ideas have been formulated by Roger Ballian and company. So he says that psi provides only mathematical Q probabilities, whereas psi completed by the specification of the measurement context, that by doing really the measurement factually, not counterfactually, then you need that to get to make sense of these probabilities. So you can say in a simple way, to make sense of the quantum mechanical formalism, one needs a state vector, psi, and also an observable or operator, where psi n is one of the eigensets. So if you have all this, you have the mutually exclusive event, and then taken together, they define what we call a physical modality. So a modality is something in a context. It belongs to an object in a context, and you need to specify the context to get this completeness of the formulation. So completing psi. So if I claim that psi is not complete, if I just get psi, do I have anything useful? I say yes, obviously. Everybody works with that. So since psi is not complete, it still says something. And what I claim is that it gives a set of contexts corresponding to all the observable or all the contexts, which include psi as an eigenvector. Where the associated measurement result is predictable with certainty. That is, this psi may appear in many different contexts. That is, this is a vector, so the vector can be an eigenvector of many different bases as soon as the dimension is large, is at least 3. In dimension 2 is trivial, but if you are in dimension at least 3, then you may have many, you know, this is a famous, I don't know whether you see my hands, but they are given a vector in dimension larger than 3. There are many different orthogonal bases to which this vector can belong. So in a recent paper, we introduced a framework which makes a careful discussion between the usual psi without a context and the physical state within a context called the modality. So in that language, psi is associated with a collection of modalities which are in different contexts, which are all equivalent. You can define that as an equivalence relation, and we call that this equivalence relation an extravalence. So it's an extravalence class. So in some sense, when the modalities are complete because they are the properties of a system within a context, but psi is not because the context is missing, but psi is a collection, actually, of different modalities, connected extravalent modalities in different contexts. So, the Einstein-Bohr debate because it confirms the incompleteness of psi. You know, the big debate was, is psi complete? And Bohr said, oh, yes, psi is complete. But he said, oh, but on the other hand, one should add the very condition for making actual prediction with psi. And if you admit that this very condition required by Bohr are the context, it means actually that if you had to add the context, and psi is not complete. So, and EPR were not that wrong actually, but you have to add something to psi. But what you have to add to psi is something which is the context, and so it means that quantum mechanics as such is complete, but psi by itself is not. This is my point. Okay. Do you still hear me? Because
yes, everything is fine. Yeah.
Everything is fine. Okay. So consequences for non-locality. So we discussed that in. So this has been discussed by many papers, obviously. So the question is: are you allowed? Should we say that predictive incompleteness is a form of quantum non-locality? Clearly, it's not related to locality in a relativistic sense, but it's related to specifically quantum properties that requires to attribute physical properties to system within context. So maybe you know Frank Laloux, so he's a well-known physicist and a friend. So for him, actually, predictive incompleteness is a form of quantum non-locality. But then it goes to definition. If you absolutely want to call that a form of non-locality, okay, then you are free to do that. But for me, the locality would be more this elementary locality, and elementary locality is okay in quantum mechanics. So, okay, so that is a question of definition. Also, an important point which should be realized, it's related to what I already said. Probabilistic completeness can be violated by a non-deterministic theory without any conflict with causality. This is what I say. But deterministic theory do agree with probabilistic completeness. And therefore, they must violate elementary locality if they want to be compatible with the violation of Bell's inequalities. So in my interpretation, this is exactly what happens for Bohmian mechanics, de Broglie-Bohm theory. It is deterministic in the sense that if you know the Bohm position, the Bohmian position, then you can predict everything in principle. So it becomes a deterministic theory. So if you assume that, then, and if you want to violate Bell's inequalities, then you have to violate elementary localities, which does not mean, I repeat it, to violate relativity, because you have no control of these lambdas in that case. But then it really creates a problem with relativity. I think Bohmians, let's say, I read paper by Bohmians who acknowledge that is, Bohm theories introduce a strong tension with relativity, and Bohmian have to think about it. In my approach, there is no tension with relativity because elementary locality is verified for any given psi. Consequence for incompleteness. So we agree that psi is predictively incomplete, but actually I don't claim that quantum mechanics is incomplete. You will see a little bit still, but certainly not in the sense of being wrong. It can be completed by many ways. So the standard way is to reintroduce the context by hand. This is just a von Neumann protection postulate and blah blah. Or it can be done in a more formal way by algebraic method. I will say a word about that. So in an algebraic framework, quantum mechanics remains universal, but there is no universal unitary evolution anymore. So this can. So I published a paper on that, which is in. I will say a few words in the following slides. And all these arguments are consistent with our, CSM approach, context, system, and modalities. So I can tell more about that if you ask. I prefer not, because maybe I think many of you already heard me in a Vagio about that. I will say a few words about that because I find it's interesting. That is to try to introduce an algebraic framework which fully complete standard quantum mechanics. The idea, I take it from a very nice paper by von Neumann in 1939, which is called On Infinite Direct Product. So direct means tensor product here. So he looks at the following mathematical problem. It's a mathematical problem. Just assume an infinite tensor product. You have many systems, and you let the number of systems go to countable infinity. Then if just spins, the dimension is 2 power n. And so the dimension 2 power n, as you say, as you know, for n equal alpha aleph 0, for then 2 power n is aleph 1. So it's uncountable. So it means that if you have an infinite number, countably infinite number of particles, the dimension of the Hilbert space is uncountably infinite, and then it simply blows up. So you cannot maintain the Hilbert space structure for infinite direct product. And I find it very nice, because if you get against mathematical limit, this fits with my context. So if you want to complete psi, you can use a tensor product between a type 1 non-commutative algebra for the system, which is just standard mechanics, and then you add this bizarre type 3 commutative algebra for the context. And if you take that all over, these things are commutative. These things just represent different states of the context, and obviously different states of the context commute, and you cannot make superposition with them. Then this provides a complete description corresponding to my modalities This algebra is universal, but clearly there is no universal wave functions because you know what happens in this infinite limit is that it blows up. The Hilbert space blows up in what is called now sectors, and these sectors are unconnected in the sense you cannot superpose them, you cannot couple them. They are sort of different blobs which have basically a classical behavior. So then this thing, obviously, in terms, it's an absolutely awful mathematical object, but you don't need to know all the details of the context. This is physically obvious. You don't need to know all the atoms of your polarizer. Since the things are disconnected, it is just enough to make a label, to give a label to one of these sectors. And then this is just what is provided by the classical description of the context. And so I'm sort of happy with that because now it's complete, given the introduction of this horrible mathematical object, horrible but manageable, I think, in an algebraic framework. So this description applies to any isolated system. So it's not a theory of everything, it's a theory of anything. You take any system, you can do that. So this is so you take any system, you type one basis, you have unitary equivalence, superposition, basis, then the famous cut or famous or infamous cut, and then on the other side, an unbounded context with an uncountable basis, loss of unitary equivalence, you cannot rotate freely, sectorization, and then since all these are probabilities, you can update. So this is, and then you have ancilla also. So when you make measurement, first you couple ancilla to your system. So still it's a system because, and there is only one cut, no Wigner friends, nothing like that, only one cut. And this goes to, because it's an unbounded site, basically. So now a measurement will look like that. So you have your system and the context. Again, this is an awful mathematical object. The coupling is awful, but for sure, what you know at the end is that you will get something like that, which is basically a superposition, not a superposition, matrices, a probability distribution over the modalities in the new context. So this calculation is basically unfeasible. It can only be done in an approximate way. But the fantastic thing is that this P does not care about the context, what happens here. You can get it directly from Gleason and Born's law by again, the square modulus of the scalar product. So you go from here. Here you see you change. You go to different sectors, and then finally you update. That is, since all this is macroscopic now, you just look at what is around you, which is this basically, and then you know where you are. It's just a probability distribution, and then you get a new isolated system, which is a new modality, is a new context. So you see, it's sort of it's what everybody is doing. But if you this calculation is unfeasible. It can only be done in an approximate way, which is what we do when we do any decoherence calculation. And then the updating is okay, unless you give a reality to the wave function. But in my approach, there is no reality to the wave function. It's just a way to calculate probabilities. What are real are the modalities, the properties of the objects. Okay, so almost as usual, but psi comes with an extravalence class, not a state. The modality belongs to both a system and a context. The cut has acquired a mathematical status. So let's go back to Bell. I'm close to the end. So I write again my 2, 2, 3, 4. This is a violation of elementary locality. So if you like it, you can take it. It will create a strong tension with relativistic causality. For me, it's to be avoided, but Bohmians like it. So why not? This is your choice. Same thing here, full predetermination, no actual randomness, to be avoided, but this is my personal opinion. Gerhard Tuff, who has a Nobel Prize, makes this choice, he likes it. So this one is the one I advocated. So it needs randomness, contextuality, but psi has to be completed by specifying the context. So obviously the trouble with that is about, let's say, realisms. And sometimes it's very close to Bohr's view, as I acknowledge that. And then some people told, then, okay, yes, but Niels Bohr is not realist. I disagree with that. But so first, let's define physical realism. What I define physical realism is the purpose of physics is to study entities of the natural world existing independently of any particular observer's perception and obeying universal and unintelligible rules. And it seems to me that this is perfectly fine for my modalities. So it means that I can keep physical realism in this definition. I can keep free choice. I can keep elementary locality. But then the description given by Psi is predictively incomplete. How to complete it? Okay, not from below, no hidden variable, but from above by specifying the context in order to get a full probability law. And then everything is sort of works, okay? Still a lot of questions, but at least it makes a framework where we sort of recover physical. It's clearly a very non-classical physical realism, but my claim is that it is still a physical realism in a philosophical sense. Okay, so that's it. Thank you very much for your attention.
Thank you very much, Philippe. So